When viewed from a distance, stars can be perceived as tiny points of light. But up close, stars are massive, seething, fiery balls of burning gas. Even though they are massive, this fierce display does not last forever. Eventually, the nuclear fusion which powers the star will burn all its fuel, thus resulting in the collapse of the remaining matter due to the immense gravitational pull. For very large stars, what happens next is a display of extremes. First, the star explodes in a supernova, scattering much of its matter throughout the universe. The star's final act is spectacular, a supernova explosion that blasts its guts across the cosmos. For one brilliant moment, this dying sun burns brighter than every other star in its galaxy combined. Then, as the last light fades to black, what's left collapses into something far stranger. The remaining matter crushes down into an object so unimaginably dense that anything wandering too close vanishes without a trace, swallowed whole by the darkness. This creation of a magnificent entity is known as a black hole. The concept of black holes actually dates back centuries. It all started in 1687 when Isaac Newton dropped his revolutionary work, The Principia, introducing the world to his laws of motion and gravity. Newton came up with the idea of escape velocity through a clever mental image. Imagine firing a cannon from an impossibly high mountaintop. He calculated the exact speed needed to completely escape Earth's gravitational pull. Nearly a century later, in 1783, an English minister named John took this idea further. He realized that if a star were massive enough, say 500 times bigger than our Sun, its escape velocity would exceed light speed. Michel dubbed these hypothetical giants dark stars, since not even light could break free from their grip. Strangely, this brilliant insight was largely forgotten for over 100 years before being rediscovered. Then, in the early 20th century, Albert Einstein developed two theories of relativity that changed our view of space and time: the special theory and the general theory. The special theory is famous for the equation E=mc², while the general theory painted a new and different picture of gravity. According to the general theory of relativity, matter and energy bend space and time. Because of this, objects that travel near a large mass will appear to move along a curved path because of the bending in space-time. We call this effect gravity. The crazy part? This affects everything, even light. When starlight passes near the sun, it doesn't zoom straight past. It bends along with the curved space around our star. Einstein published this mind-bending theory in 1915, swapping Newton's straightforward formula for a complex mathematical beast called the field equations. Then along came Karl Schwarzschild, a German physicist who took these equations for a spin. What he found would make any scientist do a double take. The math showed that if you crammed enough matter into a small space, it would create a sort of cosmic pit in space-time so deep that nothing could climb out, not even light traveling at top speed. The equations were clear, but the big question remained: did nature actually make these impossible-sounding objects, or was this just mathematical fantasy? At first, scientists dismissed the idea of a dark cosmic vacuum, a place where nothing, not even light, could break free, as nothing more than a mathematical oddity. A fascinating result on paper, sure, but surely not something that could actually exist out there in the real universe. But as the years went by, astronomers began piecing together the life and death of stars. They discovered pulsars, strange, ultra-dense stellar remnants that had been predicted by theory, and realized that if these bizarre objects were real, then maybe those dark stars from the equations weren't so far-fetched after all. That's when these mysterious cosmic traps got their now famous name, black holes. And with that, the real work began, hunting them down across the galaxy, figuring out how they form, and unraveling the secrets of their terrifying gravity. Finding something in space that swallows all light sounds impossible, right? Yet black holes give themselves away through their incredible gravity. Even though they're completely dark, their massive pull yanks on nearby stars and gas, leaving clear fingerprints of their presence. Astronomers realized they could use this cosmic tug-of-war to their advantage. By searching for stars behaving strangely, swinging around unseen companions, they could uncover hidden black holes. The perfect hunting ground. Binary star systems, where a visible star orbits side by side with an invisible monster. Binary stars are like celestial dance partners, two stars locked in orbit around each other. We can spot them in a few clever ways. Some appear to wiggle back and forth ever so slightly in the sky, while others, if we see them edge on, dim and brighten as one star passes behind the other. But here's where it gets even more interesting. Sometimes, one of those stars isn't a star at all. Astronomers have found binary systems where a normal, shining star orbits an invisible, mysterious companion. By tracking the visible star's motion and measuring its orbit, they've calculated that some of these dark partners are far too massive to be anything but a black hole. So yes, somewhere out there, a star might be waltzing with the universe's ultimate shadow, a black hole. And we know it's there, not because we see it, but because of the way its partner moves. Since we can't see a black hole, is there a way to find its size? From Einstein's field equations, we know that given the mass of a black hole, we can determine the size of the sphere that separates the region of no escape from the rest of space. The radius of this sphere is called the Schwarzschild radius, in honor of Carl Schwarzschild, and the surface of the sphere is called the event horizon. If anything crosses the event horizon, it's gone forever, hidden from the rest of the universe. Figuring out a black hole's size isn't as hard as you might think once you know its mass, and getting that mass, surprisingly straightforward. Here's how astronomers do it. 1. The space probe method. Imagine launching a spacecraft into orbit around the black hole, just like satellites circle Earth. By tracking how long it takes to complete each orbit and how far out it's flying, you can calculate the black hole's mass using the same math we use for planets and stars. 2. The companion star trick. No probe available? No problem. Many black holes have stars dancing around them in binary systems. By measuring that star's orbit, its speed and distance, you can work backward to find the black hole's mass. Once you've got the mass, plug it into the Schwarzschild radius equation, and voila, you've got your black hole's size. It's cosmic detective work at its finest. Not all black holes are created equal. Some are born from the dramatic deaths of massive stars. We call these stellar mass black holes, packing the weight of a single star into an infinitely dense point. But the universe loves extremes, and black holes can grow far, far larger. The real giants lurk in the hearts of galaxies. Every galaxy spins around a central gravitational anchor, and astronomers now think that anchor is usually a supermassive black hole, a behemoth weighing anywhere from hundreds of thousands to billions of times our sun's mass. Take our Milky Way. Its core hides a supermassive beast with the mass of 4 million suns silently steering the dance of stars around it. Black holes have another fascinating feature we can actually measure. They spin, just like stars and planets do. Think about a rotating star for a moment. If you could magically inflate it while keeping its mass the same, it would slow its spin like a figure skater extending their arms. Shrink it down, and it would whirl faster. But here's the key point. While the speed changes, the star's total angular momentum stays locked in. That's a fundamental law of physics. This spin doesn't disappear when a star collapses into a black hole. The rotation gets compressed into the singularity, creating swirling currents in the fabric of space-time itself. We can measure this spin using a clever trick. Send 2 probes skimming along opposite orbits near the black hole's edge. One probe rides with the space-time current, while the other fights against it. By comparing how long each orbit takes, the one with the current will complete laps faster. We can calculate exactly how much angular momentum the black hole contains. This swirling space-time current isn't just strong, it warps reality itself, creating a zone called the ergosphere. Here, the drag is so violent that nothing can resist it, not even light. Inside this region, standing still is impossible. Space-time itself sweeps everything along, like a cosmic riptide dragging you helplessly with it. The event horizon, the true point of no return, sits inside this maelstrom, touching the ergosphere only at the poles. Picture a black hole as the ultimate whirlpool. The ergosphere is the churning vortex that catches you, and the event horizon is the drain. Once you're caught in the current, there's no escape. Cross the horizon, and you're not just trapped, you're erased from the universe. When it comes to black holes, only 3 things matter: mass, spin, and charge. Get these numbers right, and you've pinned down everything there is to know about a black hole. At least, that's what physicists believe. This idea is jokingly called the no-hair theorem, because beyond these 3 traits, black holes are completely bald. No extra frills, no hidden quirks, just pure, minimalist cosmic destruction. Think of it like a cosmic ID card. Mass tells you how strong its gravity is. Spin reveals how fast it's twisting space-time. Charge? Well, most black holes skip this one. They're usually electrically neutral. So no, a black hole isn't a blonde, brunette, or redhead. It's more like a celestial cue ball, smooth, featureless, and utterly predictable, if you ignore the whole spaghettification thing. One final property of black holes we can measure is the electric charge. In our everyday world, most matter we bump into is electrically neutral. But black holes, they could carry a net charge, positive or negative, if they somehow hoarded more protons or electrons. Measuring this would be straightforward. Just see how strongly the black hole tugs on a magnet. But here's the catch. Charged black holes probably don't exist in the wild. Why? The universe is flooded with free-roaming charged particles. A charged black hole would act like a cosmic magnet, instantly attracting oppositely charged particles until its charge zeroes out. Nature, it seems, prefers its black holes bald and neutral. We now have a good idea of a black hole from the outside. But what does it look like on the inside? Unfortunately, we can't send a probe inside to take a look. Once any instrument crosses the event horizon, it's gone. But don't forget, we have Einstein's field equations. If these correctly describe space-time outside the black hole, then we can use them to predict what's going on inside as well. To solve the field equations, scientists considered 2 separate cases: rotating black holes and non-rotating black holes. The simpler case came first: non-rotating black holes. These perfectly symmetrical cosmic pits were easier to describe mathematically, giving scientists their first clear picture of how space-time warps around infinite density. In this case, all the matter inside the black hole collapses to a single point in the center, called a singularity. The rotating version, that came later, a much tougher nut to crack, where the black hole's spin twists space-time itself into swirling vortices. Rotating black holes have a different interior. Instead of crushing down to a single point, the collapsing matter gets whipped into shape by the intense spin. The result? A ring singularity, a perfect, infinitely thin circle of unimaginable density at the black hole's core. Black hole research continues to this day. Scientists are actively investigating the possibility that black holes appeared right after the Big Bang, and the idea that black holes can create bridges called wormholes connecting distant points of our universe. We know a great deal about black holes, but there are many mysteries still to be solved.